welcome back to another video about calculus. In this one, we'll be talking about the chain rule. The rule is so fantastic that I accidentally tried to use it before I even taught it to you guys. So, yeah, that should give you a picture of just how awesome and how powerful this rule is. In fact, the chain rule is powerful enough that once we know it, we don't really need any more differentiation rules. The ones we have already, plus this, is enough to compute all the derivatives we would ever need for this class. So what is the chain rule? Well, we have the sum rule, which addresses how derivatives work with addition and subtraction. We have the scalar multiple rule, dealing with how derivatives work with scalar multiples. We have the product rule and the quotient rule, which deal with how how derivatives play with multiplication and division. So that's all well and good. But at the start of the course, we talked about a fifth operation you can do with functions. Function composition. So that's kind of a natural question. What about derivatives and function composition? How does that all work out? And the chain rule is going to be our answer to that question. So, more specifically, we ask ourselves, given functions f and g, what is the derivative with respect to x of the composition g of f of x, which we will rewrite using the definition of composition as derivative with respect to x of g of f of x. 1, 2, 3, 1, 2, 3. Alright, and you might say, well, why do we care? Good question. Honestly, that's a question that is always welcome in my math class. Why do we care about this piece of crap? Well, okay, let's start with an example that'll kind of motivate us for this. Let's let f of x equal x cubed minus 4 squared. Alright, pretty standard function. It'd be nice if we could take its derivative. How do we do that though? I know what the derivative of x squared is, but I don't know what the derivative of x cubed minus 4 squared is. And you might have some guesses for how that would play out, but really, we don't know for sure. We don't have a rule that deals with it. Okay, but we can take the derivative kind of the quote-unquote hard way, right? We can multiply this out and then take the derivative of that. So let's try it. F prime of x is d dx of, okay, actually squaring this gives us x to the 6th minus 8x cubed plus 16. Okay? By the sum rule, this is d dx of x to the 6th minus 8 d dx of x cubed plus d dx of 16, which is equal to 6x to the 5th minus 8 times 3x squared is 24. X squared, derivative of a constant is just 0. Alright, so that's f prime of x. And that's all well and good. But again, I really wish I didn't have to expand out. And you might say, well, what's the big problem with expanding out? Well, it works great with something like x squared. But what about higher powers? So, works, but clunky. And what about maybe something like g of x equal to x cubed minus 4, even for consistency. to the 1, 2, 4, 0, 7, 1, 2, 3, 4. Well, sure, you could sit around and multiply x cubed minus 4 by itself that many times, but that's not very helpful to you, is it? And it takes years. I'm not even sure you could do that within like the actual expected lifespan of the universe. So, yeah, not necessarily a great choice there, but it would work if you had infinite time. So let's even say that's not a good enough reason to develop something for this. Let's talk about another one. Maybe h of x equal to x cubed minus 4 to the pi. Well, that's even worse, right? I don't even know what it really means to put something to the pi power. Like, sure, I can talk about it, and I know how to make sense of it as an exponent, but really what does it mean for this thing to be multiplied by itself pi times? Like, that doesn't make sense. Okay, so maybe that's a good enough reason to try to develop something like this. You might ask, well, how does finding something like this help with it? Let's see why and how. I'll rewrite f of x over here, and I'll rewrite our goal over here. Our goal is to find the derivative of something that looks like g of f of x. Or in other words, we want g of f of x to be prime, with the prime on the outside, specifically. Okay? Well, I'm going to write down a couple new functions. Maybe I write down capital F of x equal to x squared. Capital G of x equal to x to the 1, 2, 4, 0, 7, 1, 2, 3, 4. So, same power. Okay, those are all good. Maybe h of x equal to x to the pi. Now, as nasty as those two powers still are, it's just x to them. We know how to compute the derivatives of those things. F prime of x, g prime of x, and h prime of x are easy to find with the power rule. So it doesn't make sense. Why should those be so easy to deal with, and yet these so difficult to deal with using the same method? The chain rule is invented to fix that problem. Because really, right, g of x is just g of x cubed minus 4. H of x is h of x cubed minus 4. And f of x, little f of x, is capital F of x cubed minus 4. Right? So when we try to find little g prime of x, little h prime of x, and little f prime of x, we really want the derivatives of these things. Okay, the derivative of something that looks like this. So how can we go about doing that? Which side do I want to erase? Let's say this one. Let's start over with some unknown functions, so we can't try to mess around with their formulas at all. So let f and g be unknown functions. Okay? Let's let h of x equal g of f of x, which by the definition of composition is g of f of x. Our goal is to find h prime of x. And we ask ourselves, okay, how are we going to go about finding h prime of x? Let's make a quick couple of substitutions that'll help us see things better. Let's let u equal f of x and y equal h of x. Okay, so if u is equal to f of x, then h of x is equal to g of u. And we're just saying y is equal to h of x. So this combines to tell us y is equal to g of u. Okay, so those are just a couple of almost numerical substitutions, right? F of x, we're calling u. H of x, we're calling y. And now we ask ourselves, why do we do that? Well, dy du is easy to find. Dy du is g prime of u. And normally, we know how to find g prime of x, so that's all well and good, right? Or in this case, g prime of u. But we want things in terms of our original variable x, right? Because u is not equal to x. U is some function of x. Okay, so this is how y is changing with respect to u. How can we get from there to how y is changing with respect to x? Right? Using the definition of the derivative as instantaneous rate of change, we have how y changes with respect to u, because that is dy du, but we want how y changes with respect to x, which is dy dx. But since all along we want h prime of x, not h prime of anything else. Okay. But if we know how y changes with respect to u, and we want how y changes with respect to x, we need to find how u changes with respect to x. That's all we need to do, right? If I say Bob is running twice as fast as Carl, and then Sally is running twice as fast as Bob, and you ask how many times faster is Sally running than Carl, you'd say 4 times, right? Just multiplies together. That's our clue for how to deal with this, right? We want du dx. But what is du dx? Ah, we have this relationship, u is equal to f of x. So du dx is just f prime of x, which is easy to compute. We can compute f prime of x all day. Okay, and that is actually all we need to develop our chain rule formula. We're going to put all of that together to find dy dx. Alright, so the chain rule. At long last, let's let h of x equal g of f of x, composition of g with f. Then h prime of x is going to equal, well, it's the derivative with respect to x of g of f of x, and it will be g prime of f of x times f prime of x. Or in other words, let's do that same substitution as before. Let y equal h of x and u equal f of x. Then if we rephrase it, we get dy dx, so h prime of x, is equal to dy du times du dx. Change of y with respect to u times the change of u with respect to x gives you how y is changing with respect to x. And we can see that in this quote here. G prime of f of x, that's our dy du. How g is changing with respect to f of x, and then we multiply by how f is changing with respect to x. Please note, again, these are not fractions. You cannot just cancel the du's out. That's not how this works, right? These are symbols that you have to take together. But it's a good way for remembering, it's kind of like a little chain. That's how I choose to remember the chain rule anyways. And probably where it got its name from, honestly. You can chain rule as far as you want, so if you have like a double composition, you can keep chaining, everything like that. Works out exactly as you want. But this is the chain rule. This is how derivatives play with function composition, and it's all we need to unlock every derivative that we could ever want. Let's do a couple examples. In fact, let's start off with one of the ones that was giving us so much trouble in the first place. Let's let h of x equal x cubed minus 4 to the pi. And we want to find h prime of x. So, impossible to do by regular means, but with the chain rule, piece of cake. Let's let g of x equal x to the pi and f of x equal x cubed minus 4. So our trick, let g be the outer one and f be the inner one. So then h of x is equal to g of f of x, which is exactly the situation the chain rule is made to address. Okay, well, let's compute. We need g prime of f of x, and we need f prime of x. Okay, g prime of x is pi times x to the pi minus 1. But we're plugging in f of x. So we're going to get pi times x cubed minus 4 to the pi minus 1. Right? Treating it almost as if it were just an x by itself, pulling it down in front. And now we multiply by f prime of x. Fx is just x cubed minus 4, so f prime of x is 3x squared. Nice and simple. So now, just doing some algebra to simplify, this gives us 3 pi x squared times x cubed minus 4 to the pi minus 1. Kind of a nasty formula, but not really that bad. Especially because you can't do it any other way. So I think that we've gotten out pretty lucky for ourselves. Let's do another couple examples. Let's let f of x equal x squared minus 1 squared. Our goal is, as always, to find f prime of x. Let's do it the second way this time. Let's let u equal x squared minus 1. And y equal f of x. Okay, but what is f of x? F of x is just u squared. All right. Well, now dy du, or sorry, dy dx is just equal to dy du times du dx, right? That is the chain rule. But what is dy du? Well, y is equal to u squared, so dy du is just 2u. How du dx? 2x, right? Derivative of x squared minus 1 with respect to x. Okay, and now all we have to do to get y in terms of x again is we're going to plug in our definition of u. This is x squared minus 1, sorry, 2 times x squared minus 1 times 2x. And we're left with 4x times x squared minus 1. You can distribute that out if you want. I don't see the need to. There you go. Real quick, real simple. I personally prefer the second method most of the time just because that's how it gels properly with me. If you like the first one better, go right ahead. I'm not going to stop you. But yeah, for me, this just is kind of an intuitive thing to do. I put y in terms of u, or sorry, first I make my u substitution. Then I put y in terms of u, apply the chain rule, substitute back in for u at the end. And it all works out nicely. Let's do another couple of examples. Let's let g of x be the square root of x to the 4th minus 1. And our goal is to find g prime of x. Okay, try doing this one yourself. Pause the video, sketch it out on a piece of paper, see what you do, and then we'll come back and do it together. Welcome back. Hopefully you have gotten this all together. Let's do a quick substitution first to make things a little easier. G of x is x to the 4th minus 1 to the 1/2 power. I prefer thinking in fractional powers rather than with radicals. To me, it's just easier to keep track of everything. If you would prefer keeping track of the square root, go right ahead. It's equivalent to do. Okay. Now, I'm going to use the second method. Let's let u equal x to the 4th minus 1. So u is our inside here. And y equal g of x. But g of x is just u to the 1/2 power. Great. Now, g prime of x is dy dx, which is, by the chain rule, dy du times du dx. Cool. Dy du, well, that's just a simple application of the power rule. 1/2 u to the negative 1/2. Oftentimes, when you use the chain rule, that's kind of what it'll end up being. The dy du will end up being an application of the power rule. Often. At least in this class. Okay? So we have that, and that was easy to compute. Times dy dx. Okay, x to the 4th minus 1. 4x cubed minus 0. And now all we have to do is back substitute. This is 2x cubed times x to the 4th minus 1 to the negative 1/2 power. If you wanted to get real fancy, you could write that out as 2x cubed divided by the square root of x to the 4th minus 1. There we go. So, again, the chain rule makes computing very nasty derivatives very, very quick and very, very simple by computing two smaller and easier derivatives. Let's do another couple of examples. Maybe we'll do another one using the first method and another one using the second method. Let's let f of x equal x cubed times x cubed, now x squared plus 3 to the 7th power. And we want to find f prime of x. Okay, we're using an f instead of an h, but I see no problem with that. Right, let's let g of x be our outside, which will be x squared plus 3, or sorry, x to the 7th, and h of x equal x squared plus 3. Alright, so we're taking care of this chunk, and you might say, well, what about this part right here? That's going to be dealt with by the product rule. So, f prime of x is the derivative with respect to x of x cubed times x squared plus 3 to the 7th power. Now, by the product rule, this is equal to first times derivative of the second plus the second times the derivative of first. And this part is going to be no trouble to compute at all. So let's ignore for now, and let's say this is x cubed times derivative with respect to x of, using our standard compositions, g of h of x. Yes. Plus, okay, this is going to be 3x squared times x squared plus 3 to the 7th. So, second chunk already done. Don't even need to worry about it. Chain rule will address this first part. This is equal to x cubed times, by chain rule, g prime of h of x times h prime of x. Plus 3x squared times x squared plus 3 to the 7th power. So far, going pretty well. let's find those two things. That's equal to x cubed times, okay, g prime of x is 7x to the 6th power. So g prime of h of x is just plugging h of x into here. So it'll be times 7x squared plus 3 to the 6th power times, okay, h prime of x is just 2x, follows very quickly from the sum rule, times 2x. And then we still have that second chunk over there. 3x squared times x squared plus 3 to the 7th power. Cool, we're done with all the calculus. Now it's just some algebra to simplify. This gives us 14x to the 4th times x squared plus 3 to the 6th power plus 3x squared times x squared plus 3 to the 7th power. That's done. If you wanted to, you can factor stuff to make that nice. That would give you in x squared times x squared plus 3 to the 6th times 2x squared plus 3. Yep. 3 times x squared plus 3, which you could further simplify as x squared times x squared plus 3 to the 6th plus, okay, 5x squared plus 9. So, either one of these are acceptable answers. Leaving like that is just fine to me because it clearly honestly shows where everything came from. This is clearly something with the product rule because it's got that little plus there with that kind of pattern. Maybe I shouldn't say clearly. It's clear once you've done this for, enough years. But yeah, all in all, not that bad of a derivative, even using the first method, which in my opinion is slightly messier. We choose the proper substitution to deal with the hard part. The product rule gets it to, okay, we're just dealing with that hard part and then easy part. Easy part, done. Hard part gets taken care of by the chain rule. Boom. And then after this point, all of it's just algebra. Let's do one more example. And I'll do it using the second method. Alright, let's let h of x equal x divided by 4x plus 1 all cubed. And our goal is to find h prime of x. Alright, so here's what we're going to do. Let's do a quick substitution. There's a clear inside and outside. Let u equal x over 4x plus 1 and y equal x cubed. Or sorry, not x cubed. H of x, which is u cubed. Great. Well, now h prime of x is dy dx, which is dy du times du dx. dy du is just 3u squared, so that's all nice and easy. That part, done. Now we just need to find du dx. Times ddx of x over 4x plus 1. Bad, but not that bad. How do we deal with a fraction taking the derivative? Simple. We apply the quotient rule. So this is 3u squared. You could plug back in u here. I choose not to because it'll just make it more compact as we write it all out. And then I'll plug it back in at the end. So 3u squared times bottom times the derivative of the top minus the top times the derivative of the bottom, all divided by the bottom squared. Cool. We're nearly done with the calculus and on to the algebra. Once we're back in the territory of algebra, we're kind of safe. I say safe. That's actually where a lot of mistakes come from, is people make algebra mistakes and not calculus mistakes. I'm prone to doing that, as you guys have seen. But we're safe conceptually, in theory. Okay, let's compute this. This is equal to 3u squared times 4x plus 1. Derivative with respect to x of x is just 1, so that's gone. Minus x times that derivative there. That derivative is just going to be 4, right? Using the scalar multiple rule, power rule, and sum rule. We're left with minus 4 times x. All divided by 4x plus 1 squared. That gives us 3u squared times 1 over 4x plus 1 squared. And now if we just plug back in what our u is, that's equal to 3 times x over 4x plus 1 squared times 1 over 4x plus 1 squared. Doing all the nice fraction arithmetic gives us 3x squared over 4x plus 1 to the 4th power. Well, it's a good thing the lesson's done, so I don't need that chunk anyways. Alright. I think that's a nifty example and shows, hey, even when we have a more complicated relationship between u and x, chain rule still takes care of getting us to that point, and now we're just taking the derivative of something we already know how to deal with using the quotient rule. As much writing as the quotient rule might be. So yeah, that's it for rules of differentiation, and in the next chapter we'll start talking about, okay, this is how to differentiate things. Why do we actually care about differentiating things? What can you use it